Okay, so terminology review. Okay, so let's say an n complex is pure if all of its facets have the same dimension. So n complex means the largest facet has dimension n. Pure means they all have a dimension n. And everything we talk about here, at least in this lecture, not in the entire course, the complexes are pure. But I'm going to mention it just so that the theorems are correct. So we're going to define notion of a codimension. So if you have an n simplex, an n complex, and an m simplex, the codimension is the difference. And so I'm going to talk about the codimension of a simplex sigma because it'll often be clearer than just writing n minus m, because I don't want to always have to write to the m. And so I'll explain when that shows up. Remember, a carrier map maps one complex to another by taking each simplex in here and mapping it onto a subcomplex there. So the input to a carrier map is a simplex, the output is a subcomplex. Yeah, animation's not quite right here. So if X is a pure shellable n complex, and M is which sends X to a Y, is a carrier map that has the property that on every simplex S, the image of S is K minus codimension sigma minus 1 connected. Okay, so what does this say? Well, this says that if sigma has dimension n, then the codimension is 0. So that says that if sigma is a facet of X, then it's K minus 1 connected. So it sends each facet to a K minus 1 connected subcomplex. And then if you look at a face of sigma, when you drop down one dimension, your connectivity drops down one dimension. But, and so on. So that's all that this is saying. So this is just compact notation to say stuff that would be even worse if we wrote it out more in longer terms. So we take each simplex here, we send the top level the K minus 1 connected subcomplex, and every face to a lower amount of connectivity. When the codimension is K, so when we drop down K dimensions, well, all we're saying here is the image is non-empty. If we drop down more than K, then it could be empty, it could be anything. Because when we say, when the connectivity goes below minus 1, then it's a vacuous statement, doesn't say anything. Oh, and then the actual theorem is that the image of the entire complex is K minus 1 connected. So this is a local statement because it says that this talks about how the carrier map acts on each individual simplex. So locally, it sends each simplex to a connected subspace, to a connected subcomplex. How do they glue together? Well, we know that X is shellable. So the fact that X is shellable and that the image of each individual simplex is connected means the image of the entire thing is connected. And so this is the argument that we're going to use to show that round operators preserve connectivity. So this is a little bit of a technical lemma. In a minute, we'll come up with a theorem that's more general. So here is where we're going to exploit the shellability. So because X is shellable, we can write it as the union of its facets. And the indexing is the shelling order. So we hypothesize there is a shelling order. This is it. Because these are facets, the complex itself is the union of its facets. Okay, and now we're going to argue by induction on T. So for the base, when T equals 0, well, our hypothesis, remember, is that acting on an individual simplex, M is K minus the codimension of the simplex minus 1 connected, but a facet by definition has codimension 0. So this is the base case. So that just says that it's a K minus 1 connected. So the base case of the induction is pretty easy.
Why does it say that it's K minus 1?
Oh, because our assumption here, our hypothesis is that this is a single simplex. So m applied to a single simplex is k minus the codimension of that simplex minus 1. And the codimension is the difference between the dimension of the simplex and the dimension of the complex where it lives. But this is a facet, meaning it has maximal dimension, which means that the codimension is 0. So it says that this quantity here is 0. Again, just by hypothesis, because it's a facet. So the codimension measures how far the dimension of the simplex, how far below that is from the maximum simplex that contains it.
But you don't want to show that m of x is now k minus 1?
Well, we're going to prove that m of x is k minus 1 connected. But what I'm going to do is so x is the union of these things. So what I'm going to do is I'm going to prove by induction on T that bigger and bigger unions are k minus 1 connected. And then when we hit T, that's the entire thing. So we're going to build this up inductively.
I see.
This is the case when we have just one facet.
Yeah, so we're proving something slightly stronger, which is that every prefix of the Schelling order gives you.
Now you have only one.
Yeah. So our induction hypothesis is that if we take the union, remember that carrier maps have the property, the meaning of the union of m applied to a union of things is the union of m applied to the things. So we're going to assume inductively that if we look at the image of the first t minus 1, that the result is k minus 1 connected. So we did the induction case, and now we're going to assume this as our induction hypothesis. And we're going to call that k, just for short. And that's k minus 1 connected by the induction hypothesis. And I'm going to look at the image of the very last simplex, and I'm going to call that L. So we have a k and L here. And that's k minus 1 connected also by the induction hypothesis, because there's only one, by the theorem hypothesis, because our theorem says that the image of each individual facet is k minus 1 connected. So we have our complex is the union of k, which is k minus 1 connected, and L, which is k minus 1 connected. And so now what I want to do is I want to look at the intersection of k and L and ask about that connectivity. So here is k, if we write out k intersection L, this is k and that's L, and we have the intersection here. So what I can do is I can move the parentheses around and get this statement here. It's the union of each of these intersections.
In which the I was 0.
Oh, yeah, that's right. This is a PowerPoint failure. There's also a missing I down here. But so this goes from I equals 0. So here, because we can move intersections in and out of carrier maps. So we end up with union I equals 0 to of this thing here. So then the next thing that we do is we're looking at the image of all these intersections, but because this is this is shellable, this is the same as m of psi of I, where psi of I are a set of faces, maximal proper faces of phi of t. So remember when we glue each simplex on, the intersection is some set of n minus 1 faces. And so this is the image of some collection of n minus 1 faces. So it's a set of n minus 1 faces for some non-empty index set.
Can you repeat this?
So what we're doing is, so here I just moved the parentheses. Okay, so here I'm saying I'm looking at the image of all these intersections. But what do we know about the intersections? Well, in fact, the small intersections are absorbed by bigger intersections. So the only thing we care about are the big intersections. And the big intersections are all n minus 1 faces. So whatever the union of these things is just a set of n-1 faces of phi of t. And so I call these things psi of I. But psi looks kind of like a phi. And so the psi of I is a set of maximal proper faces of phi of t for some non-empty intersect index set. So then what we can do is, so this is a cover. So K of L is the union of these things, and that's a cover for those. And so anytime you see cover, you say, oh, nerve theorem. And so I'm going to define psi of j to be the union of psi of little j's, where j in the big index set j. And the intersection here is the same as, so the intersection of this, since we can move intersections around, we get m of psi of j. So in some sense, the nerve, some of the nerve structure is preserved when you apply this map to the complex. And so psi of j has codimension size of j in x, because when we take faces, if we take n-1 faces and we intersect them, if we intersect any two n-1 faces, we get an n-2 face. Any three of them, we get an n-3 face, and so on. So that, this is just how faces in simplexes work.
How do you know the product of the
Oh, because these are faces of a single simplex. So we're looking at sets of size sets of size n on a ground set of size n+1. So if we have any two distinct ones and they intersect, you're going to lose. It's going to drop down by a size of by 1. So this works because we're talking about faces of a single simplex. So what we're doing is, yes, so this is, so phi sub j has codimension size of j, because we lose, that's how many vertices we lose when we take these intersections. And, but each one of these is a single simplex still. It's just a smaller face. And so by hypothesis, M acting on a small simplex is K minus the codimension minus 1 connected. That's the theorem hypothesis. This is why we put codimension in there, so that we can do these kind of inductive arguments, because we care about how it behaves on smaller simplexes. So we know that the image of each of these intersections is, that's how connected it is. But these are exactly the conditions. So the animation is out of order. So the psi sub I are faces of phi, which means that phi sub j is this dimensional face, which means it has this codimension, which means that this is connected by the theorem hypothesis. So we can apply the nerve lemma to this. And so this is the cover. These are the vertices of the nerve. These are the simplexes of the nerve. This is the connectivity. And if we look at the original formulation of the nerve theorem, this is K minus 2 is the, we rearrange it so it kind of pattern matches the original statement. And from this, we can say that K intersection L is K minus 2 connected if and only if the nerve of the covering is K minus 2 connected. So again, we're taking, we're looking at the fact that the image of a nerve is still a nerve. So we're about to apply the nerve lemma to this cover. We've established this condition here. Now, how many vertices does the nerve have? Well, whatever this index set is, however many faces the intersection is, we don't know how many, we know it's non-zero. However many they are, that's the number of vertices in the nerve. But we know that any k of them form a simplex. Because if you intersect k of them, then your k minus the codimension minus 1 connected, which is always greater than minus 1 if there's a k of them. So the nerve contains a k-1 skeleton of of an I simplex, but which means it's k-2 connected.
Can you repeat the last box?
So we've established, we want to show that this intersection is k-2 connected. That's kind of our sub-goal. And that is true if and only if the nerve is k-2 connected. So we want to show that the nerve is k-2 connected. Now, what is the nerve? The nerve is, each element of the cover, each of these is a vertex, and each intersection of these things is a simplex of the nerve. And it's a simplex if the intersection is non-empty. So the question is, what are the non-empty simplexes in this nerve? Well, how many vertices are there? Well, there's one per face here. So we have some index set I, which is non-empty, could have one element, could have up to n elements, no more. And so that's how many vertices there are. And so what I want to know, in order to know whether it's k-2 connected, I don't need to know about the entire thing. All I need to know about is the k-skeleton. And so if I take the intersection of any k of these things, so if suppose J has size k, then it's -1 connected, which means non-empty. So I know that if I take the intersection of any k of these covers, then the result is non-empty, which means that every k vertices of the nerve defines a simplex. And so I have this many vertices, and every k of them is a simplex, which means that this contains the k-skeleton of a simplex with this many vertices. But the k-skeleton or the k-1 skeleton of that size simplex is always a k-2 connected. So that says that the nerve is k-2 connected, which means that the intersection of k and L is a k-2 connected. So this is our sub-goal. So we're still not done, but we're almost there. Okay, so what I did was I gave you a cover. I gave you K, which is everything up to T, which is k-1 connected by the induction hypothesis. I'll give you L, which is the next piece that we want to put together. So that's k-1 connected because this is by the theorem hypothesis. I want to compute the connectivity of their intersection. And I've just argued that that is k-2 connected by this application of the nerve theorem. And so if I know that this is k-1 connected, that's k-1 connected, and the intersection is k-2 connected, then it follows by yet another application of the nerve theorem, this one almost trivial, that their union is k-1 connected. And so that's the proof.
For this, you don't need all the machinery of the nerve. It follows from simpler.
Well, for this one, yeah. Yeah, but the only thing I've talked about is nerve theorem. So the hammer and thumb argument. But yeah, there are simpler ways of getting from here to here. But the simplest is you can just believe me. Okay, so that was a technical lemma. And so now we're going to get to the actual stuff, which is actually simpler than that. So here we are back at we have our complexes that represent the state of the world after each number of rounds. We have round operators. And so the main theorem says that if for each R sub I, the image of a single simplex is a shellable complex, which sends each facet to something of a dimension at least k. And then if you're looking at faces, then we basically subtract the difference in the dimension. So if this is true, then the composition of all these things is k minus codimension minus 1 connected. So in order to prove things like impossibility of set agreement, we want to show that this is highly connected. And this says if you want to do that, all you need to prove this local property about each round operator. And if that is true, then taking a single simplex and applying the whole sequence of round operators will give you something that is disconnected. And if you start out with a facet, then this will be k-1 connected. And this is what we really want, because this says that we can do round by round invariance arguments. You know, all we need is to be able to show that locally this is shellable. Okay, so here is the proof, which is relatively short and painless. So we're going to do reverse induction on R. That is, I'm going to start here and then work backwards. So the base case, by hypothesis, if I apply one round operator on a single sigma, I get a shellable complex of the right dimension, because I just assumed that as the hypothesis. So R of R is k minus codim minus 1 connected because it's shellable. Okay, so now for the induction step, I'm going to call this composition here R star, just to keep the notation from driving us crazy. So the induction hypothesis here is that for any tau in C of L plus 1, R star of tau is a shellable of the right dimension. So that's what we've established by induction. And what I want to do is I want to grow it backwards one round and show that this is still true. The theorem hypothesis says that if I go back here to C of L, applying R of L to a single sigma shellable of the right dimension. So this works and this works. Now I want to show that the composition works. And the previous lemma, if I replace, the previous lemma basically says that the composition is k minus codim sigma minus 1 connected, because the previous lemma says that if I'm operating on a shellable complex, then each individual simplex is a k minus codimension minus 1 connected. So the previous lemma was we did all that work in order to get here. That's the proof. So this is what so this is the main thing. When we look at specific models of computation, we need to show that each round operator acts on, we analyze how each round operator acts on each individual simplex by showing that it's shellable, which is all the work. And the fact that it has this dimension is usually trivial, because you just count how many processes there are, and that gives you the dimension. So what I think we'll do next time, I'll give you a quick preview of what's in store.
So what's the minus 1 confuse me? Induction hypothesis just tells you that the induction hypothesis tells you that R star is k minus codimension minus 1.
Oh, so the so the previous theorem says that your k minus so that says that if this is shellable, then if X is shellable, then we have a carrier map that sends each individual simplex to a complex that is disconnected. So if it's shellable before, and the image of each simplex is shellable, then the combination of things is shellable. And so this is how connected we want it to be, k minus codimension minus 1. And then this is going to be, for the induction hypothesis, this is going to represent all of the future rounds that we haven't done yet. And then this x is going to be the effect of applying one round to a single simplex and then composing them. So this is kind of long and technical, but each of the steps I think is pretty straightforward. It may be harder to appreciate this sitting here in real time, but it's so this is the x in the previous theorem. R star is the map M, and we know this is shellable because this is the image of a single simplex here. So what? So for all that work, question is, well, what is it good for? Well, what I'm going to do is I'm going to show you that just about all of the kind of classical models that we've looked at correspond to round operators that have shellable complexes. And it's an interesting question, why do all these things that show up in nature turn out to be shellable? And I don't actually know, but they do. And so what I'm going to do is look at each of these models and prove that the one round operator acting on a simplex is shellable of the right dimension. And then we can, in the synchronous models, what will happen is the round operator will kill some number of processes, so you can run it for some amount of time until you run out of processes to kill. That'll give you a round basis. For semi-synchronous, where we have real time, what I'm going to do is show we can preserve connectivity for a certain amount of real time by a combination of stretching arguments and topological arguments. When we get to shared memory plus k-set agreement, then things get a little bit slightly more involved, because it turns out the complexes themselves are not going to be shellable, but they are the union of shellable complexes, and this union is itself shellable. So in this mixed model, we have to sort of move the entire argument up one level and talk about the nerves being shellable instead of the actual complexes being shellable. But it's not as painful as it seems. So what we'll do is, so next time I'll talk about the different models and stuff.
So in what way can a complex not be shellable?
Here's a...
This is coming to our last question, why everything that arises in nature of
Okay, well, so here is a non-shellable complex.
The invisible version.
So that's not shellable because the intersection, you can't build it by gluing on large faces. And there was actually a question that took a minute for me to answer that someone asked. Is suppose I take a bunch of, so if I build these things up to make things shellable, and then I glue this edge to that edge, why isn't that shellable? Because I said before that a shellable complex is just topologically it's a wedge of spheres, and this is not a wedge of spheres. So it can't be shellable, so why isn't it shellable? It certainly looks shellable. And the subtle point has to do with the fact that if I want to take this triangle and I want to glue it here and glue it here, but this point and
Another marker there which might be more visible.
I think all of these markers are pretty worthless.
Yeah.
But the problem is that if I want to sort of glue this this way,
you need to turn them around.
turn them, whichever way I do it, I'm actually taking two distinct points and sort of surreptitiously gluing them together. And so I'm violating the shellability rule in a subtle way. So that's a non-obvious example of something that is not shellable.
And when you remove the containment,
So the
become non-shellable?
No, so in the specific examples that we look at, there are theorems that basically say that if your minimal core size is C, then that gives you a certain number of dimensions to work in. And I think if you don't have the containment requirement, then you're not guaranteed that you have those dimensions to work in. And so the proofs don't go through. But it's one thing I'll think about is try to identify exactly where it breaks down. But what we're saying is that if you have minimal size C, then I can fail some number of processes within that range. But I can't necessarily do that if I have to fail all of them at once, for example. So if I can't fail a subset. So you don't have the kind of flexibility you need to make these arguments hold together. Okay, so see you all in 2 weeks.